We have been looking at Fick's law with the hope that we should be able to relate the diffusion mass flux to the concentration gradient, so that we would now reckon the concentration gradient, let us say in terms of a mass fraction, as one of the primary unknowns. Then we should start thinking about what would be its corresponding equation. Okay, so when you now want to solve the combustion problem, that means you have to actually find out how the composition of your mixture of reacting species changes. So your reactant the species concentration is an unknown, and therefore correspondingly you need to have an equation that determines it, and the equation that we will be looking for is the equation of conservation of mass of species A. This is a general mass conservation equation for a particular species as an extension of what we have already seen before in the case of the thermochemical processes that we have looked at, like constant volume, constant pressure, fixed mass reactors, and the well stirred reactor and so on. So there we had a very limited approach to conservation of species mass, but here we will try to actually have the most general approach that is possible, that would include convective effects as well as in the most general way, as well as diffusion effects, right. So we want to now bring those into account, in addition to unsteady effects that are possible and chemical reactions, right. So the way we want to do this is to now consider a arbitrary volume. So we can now look at this as like a volume. So the shading basically is to give a 3D effect. The surface is denoted by sigma, and the volume itself is denoted by script v, and so we consider an arbitrary control volume. I would like to emphasize that the arbitrariness of the control volume is pretty important for us, okay, and that's what actually tries to make it quite general for us, and we will probably try to get the same equations in the end, but we will invoke the arbitrariness of the control volume to do this pretty soon. So then the question is, how do you conserve mass? The answer is just like you conserve anything else, okay. So how do you conserve anything? The answer is, so you now look at a situation like let's say a control volume, and then you have to now keep in account the rate of change of whatever you want inside the control volume as equal to whatever is coming from outside versus what's going out, what's coming in, okay. So this is pretty general, as I have said earlier. You know to do this from looking at your bank account on how much money you have, like versus how much money is getting depleted versus what's coming in and what's going out and so on. So this is a very intuitive idea, nothing greatly mathematical about it. So what we will first do is write the conservation equation like a sentence, okay, like a verbal statement, so that it just appeals to us, appeals to a common sense without getting into mathematical notation. So here, rate of species A generated slash consumed by chemical reaction in volume V, is equal to rate of species accumulated or depleted in volume V plus rate of species entering or leaving, right, entering or leaving the surface sigma. Okay. So there are three things that are happening primarily. One, you have species getting generated or consumed within this control volume, okay, and you have species coming in and going out of the control surface. So if you now look at how much of your species A, so we are looking at a particular species A, okay, so whenever we say C species we should be looking at species A here, right. The amount of species A, mass in this case, okay, when we say amount we are looking specifically at mass of species A that is accumulating or depleting, the rate at which it is accumulating or depleting, how much of it is growing or decreasing. It depends on how much of it is generated or consumed within the control volume, okay, plus how much of it is entering or leaving the control surface. So in other words, we will now see that there are these three things, right, generated or consumed, accumulated or depleted, entering or leaving, and you have all these things with a slash in between to say this or that, and you can always look at whatever is on the left hand side of the slash, they should kind of go together. That is, if something is generated, okay, or entering, it will get accumulated. If something is getting consumed, that is, it disappears, or it leaves, it will get depleted, okay, they all go together. So this is fairly straightforward for us, okay. The second thing that I would like to point out in this verbal equation is two of them are happening in the volume, the other thing is happening across the surface, okay. So keep this in mind, we will have to apply the Gauss's divergence theorem to convert the surface term to volume term. That's why I'm basically looking at this, okay. So this can be now written as then a integral over the volume dou rho A over dou T dV plus integral over the surface m dot s vector dot n hat d sigma equal to integral over the volume WA dV. Alright, here this is the first term on the right hand side of the verbal statement, which is to say the rate of accumulation or depletion. So how did you get this? Rho dV is the mass in an elemental volume that's inside this control volume. So you now have a dV that you want to integrate over the entire volume ultimately. So rho A times dV, so rho is the density, the rho A is the density of species A times the elemental volume is the elemental mass there, and dou by dou T of that is the rate of mass accumulation or depletion, right. We don't want to worry about the dV being changing in time because that's like fixed in time. So the only thing that's changing is the density itself, right. That's like the mass concentration, as I said. So the concentration of the species is changing in time, and so this is the rate of accumulation or depletion term. That's a volume term. We can see that that's a volume integral. The rate of mass entering or leaving the control surface is the second term on the right hand side of the verbal statement, which we now put on the left hand side of the second term here. So this m dot A is the mass flux, okay. So we have looked at this as a mass flux. So essentially what happens is, if you now were to look at a little window on the surface as a d sigma, this has a m dot A vector mass flux that is cutting across at an angle to, let us say that's your n hat. If this is your unit normal locally, alright, to this elemental area d sigma, which we want to now integrate over to get the entire sigma. This is the mass flux that we are looking at, that's going at an angle. So if you want to now look at the projected mass flux that's coming out, that should be the dot product there, right. And this now takes care, the dot product will actually take care when you now integrate over the entire surface, whether it's going to leave or enter, it will take care of that, okay. So the dot product could be negative or positive depending upon whether it's going to be entering or leaving, okay. So here WA, as we know, is the reaction, this is the mass reaction rate, this is not the molar reaction rate, okay. We are looking at the amount of mass that is produced per unit volume per unit time. So this is actually going to be, the units is going to be kgs per meter cubed second, right. So this is not to be given by the law of mass action and Arrhenius law. You need to use that expression and multiply by the molecular weight of the species A in order to get this, because this is mass, alright, keep that in mind, alright. Now so we now notice that two of them are volume terms, this is a surface term, therefore we now use the Gauss's divergence theorem to convert your surface term to a volume term as well. And so we now have a volume term for the first as before, plus a volume term for the second as well now, which is divergence of m dot a vector dv equal to integral sigma over volume WA dV. So what you can do is group all of them, rho a dou rho a over dou t plus divergence m dot a minus W a dV equal to 0. Here is where we now invoke the arbitrariness of the shape of the control volume that we have considered, okay. Now if this integral has to be 0 over this integral for the entire volume for any arbitrary volume in general, that's possible only if the integrand is 0, right. So we now get from here, for any arbitrary control volume, the above can be satisfied, the above integral, we should specifically say the above integral equation can be satisfied only if the integrand equal to 0. So that implies dou rho a over dou t plus divergence m dot a vector is equal to WA. Alright. We are still not quite looking at the three fundamental processes of combustion showing up here, although we see three terms, okay. This is a unsteady term, but this actually embeds convection and diffusion together, because we now notice that this is actually corresponding to a rho a VA vector, where VA vector is the velocity of species A in a laboratory fixed coordinate system or a stationary frame of reference, okay. And then we will now have to split it into the mixture average the mass average velocity of the mixture and its diffusion velocity. When you do that, then we will get into a convective term and a diffusion term separately, in addition to the reaction term that's showing up already. Okay, then we will begin to see the three basic processes: convection, reaction, diffusion, reaction. Okay, so that's where we are heading. We can now do this for species B. Okay, so let us say we now say similarly. Species B, do we have to do this again? Shall we? Right. So how would I do this? All I'm just going to do is wherever I see A, I'm just going to replace that by B. That's that simple. So I can write dou rho B over dou T plus divergence m dot B vector is equal to WB. Now let's just go back and call this equation 1 in this class, and let's call this equation 2. Okay, let's now try to use Fick's law. Okay, using Fick's law, for a binary mixture of species A and B. Okay, that's the reason why we wrote another equation for B. It's not like we want to have fun with all the letters in the English alphabet and so on, right? So if you now have a Fick's law, then how does this work out? We can now say dou rho A over dou T plus divergence rho A V vector equal to divergence rho DAB gradient YA plus WA, and dou rho B over dou T plus divergence rho BB equal to divergence rho DAB gradient YB plus WB. All right. Is there a problem? I guess not. We had a m dot B. Let's pick m dot B in this panel, and m dot B is a rho B VB vector. Okay, so VB vector could be now written as V vector plus capital VB vector. Okay, so you now write, split that, and then you now get your rho B V vector. This is the mass averaged velocity of the mixture of A and B. Then you have the other part, you have the rho B capital VB vector, and that is actually JB vector. For JB we had a negative rho DAB gradient YB. Alright, and you now try to take it on the right hand side, you now have a rho DAB gradient YB. We already had a divergence, so we now have the same thing outside. Alright, so this is how we have actually got these two equations. Now what happens when you try to add these two? So here, okay, before we do that, so we can now begin to see that this is the unsteady term. Okay, that's because the process could be unsteady. We now have a rate of depletion or consumption of A, so depletion or generation of accumulation of A in an unsteady process. So this is an unsteady term. Okay, so you can now say this is unsteady term, right? This is the convection term, right? heat transfer people might probably use convection for natural convection, okay, but aerospace people are used to forced convection most of the time. So and then they might call this advection, okay, so we are convective people, so we convect so all the time, therefore this is, we just call this convection, and this is the diffusion term, right. If you want to now generalize most conservation equations, well you would have an unsteady term, all right. Let's say for example looking at a momentum conservation, you may have an unsteady momentum term, you have a unsteady momentum convection, sorry, you may have a momentum convection term. This would be diffusion, that would be a viscous effect, okay, and then this is the reaction term in our case, but in general this diffusion term could be referred to as a transport term, okay, and the reaction term could be referred to as a source term, okay. And in the case of momentum, for example, a body force could be like a source, but in this case the chemical reaction provides a source. So these are typically what's going on. So primarily what's happening is you have a convection, diffusion or reaction that's coming up, that constitutes your combustion process. This is something that we have seen in the past. Alright, now let's try to do some interesting thing here. Let's try to add up these two equations, right. Add the above. What would you get? You have a partial derivative of rho A with respect to time plus partial derivative of rho B with respect to time, that's dou by dou t of rho A plus rho B, okay. You now are looking at a mixture which has only two species, right. So rho A plus rho B is nothing but sigma I equals 1 to 2 of rho I. What is that? That's just a mixture density, rho. So rho A plus rho B is equal to rho. So effectively you now get a dou by dou t of rho by dou t, right. So you now get dou rho by dou t plus, you can do all the summation, all that stuff through divergence and so on, no problem. So divergence of rho A times V vector plus divergence of rho B times V vector is nothing but divergence of rho A plus rho B times V vector. So rho A plus rho B is again rho, so this is divergence of rho times V vector, right. So this is divergence of rho V vector equal to, let's look at what happens here, right. Divergence of rho dAB, well if you're very picky we should probably put dBA here, right. We just wanted to, like a computer, we wanted to wherever you got a here we put a B and vice versa to construct this equation, right. So we should have put dBA, let's do that, but then we notice that dAB is equal to dBA, we saw that the other day, right. And so these two are the same, rho is the same in both, and then you have a gradient. So all that is going to happen is divergence of rho dAB times gradient of YA plus YB. What's YA plus YB? That's 1. Okay, you now have a mixture and YA and YB are mixture fractions, okay, and this mixture has only A and B, so the two fractions together should become unity, right. And what is gradient of 1? 0. Okay, so you now get a 0. What does that mean? Is it because gradient of 1 is equal to 0 that we get this addition, right? It actually tells us the same thing as what we saw the other day for dAB equal to dBA. If species A is mixing into species B, then species B is mixing into species A. They are just having fun with each other, nothing else is happening outside of this. So you don't have a extra so notice that this and this are actually coming out from surface terms, right. So it's as if like these two together are all happening inside. There is no extra mass of the mixture as a whole that is entering or leaving because of the diffusion process. If you now put things together, right. So that's exactly why the diffusion fluxes, the diffusion mass fluxes of all the species together will equal to 0. It all looks like they are all interacting with each other, but the sum effect, the net effect of this is nothing. There is really no net mass exchange by diffusion of all the species put together in a mixture. Okay, this is a very important idea that comes out of what we are doing here. Plus, what do you get for WA plus WB? Can we just write that there? If it were an n component mixture, right, where we had subscripts like I for the ith species equation, we would have written like sigma I equals 1 to n Wi would be. Should we? Can we? We did it in the past. We had the sigma I equals 1 to n. The question is, did we have a Wi or did we have an omega I? And does that matter? Greek or English? Did that matter? Didn't matter? If you were to be looking at omega I, that's the number of moles of species I produced per unit volume per unit time. Okay, and you try to sum over all the species, you might find that there is like a net mole production in this reaction that we are looking at. Okay, but here we are looking at W, which is the mass that's produced per unit volume per unit time, right. So if you now try to add up the mass that is produced or consumed, okay, keep in mind things have to get consumed if things have to be produced, right. If mass of species I produced per unit time, produced or consumed per unit time per unit volume, plus mass of species B produced or consumed per unit time per unit volume, right, what would that be? That should be equal to 0, because if you can't have A depleted or consumed, you can't have B produced, or vice versa, as far as mass goes, because mass is conserved in a chemical reaction, because chemical reactions are only based on electron exchanges and nothing to do with nuclei, right. So you get a 0 again. Okay, so doesn't look good to have an equation with 2 zeros right next to each other. It's sufficient to write 1. And what do we have? Do we recognize this? Yeah. So this is basically your continuity equation of the mixture, as if there was no diffusion going on, no reactions going on. So when your aerodynamics professor writes this equation for flow past an airfoil, okay, airflow past an airfoil, right, you could strictly speaking argue with him or her that there could be chemical reactions and diffusion of species going on and you wouldn't know, would you? Right, that's as far as the mixture is concerned. Okay, the mixture doesn't really feel these things. As far as the mass of the mixture, mass conservation of the mixture, you will find that there are effects in the energy of the mixture and so on. Okay, but as far as the mass of the mixture is concerned, it didn't matter that you had a multi-component reacting flow. Isn't that kind of interesting, right? So you get back your mass conservation of a mixture as if it's a non-reacting single component situation. Okay. Now for fun, let's also have one more thing that we can do. We could we could write conservation species conservation equation. We will simply call the species conservation equation. That's the stuff that we have done here. We'll simply call this a species conservation equation. Okay, so we could write a species conservation equation on a molar basis. Okay, we will pretty much get the same thing, except that we will just change our notation. We will not use rho, we will use C, we will not use M, we will use N, we will not use W, we will use omega, right? So simple, right? So we could write dou CA over dou T plus divergence NA dot vector is equal to omega A, alright. Can you do what I said before? What will happen? If you now write the same thing for species B and you look at only a binary mixture, okay, what do you think will happen? You will get CA plus CB is equal to C, right? And you can also get a similar expression over here. We won't recognize this because we never really do a mass conservation kind of thing for mole conservation for a mixture or a non-reacting single component species flow, right? But then what's going to happen is this two terms, the corresponding two terms for this, we will have a XA and a C, we will have a XB and a C, right? You now add these two, you will still have 0 because you're now going to get like gradient of XA plus XB, which is 1 again, right, just like YA and YB, right? So this is going to be 0, but omega A plus omega B is not going to be 0, right? That's the only difference. Okay, now you can do a couple of you can do one more thing. We will have a we will have a V star, we will have a CV star, okay, keep that in mind. So using Fick's law we get dou CA over dou T plus divergence of CA V star, which is the molar averaged mixture velocity, equal to divergence of C DAB gradient XA plus omega A, right? Now for a quiescent non-reacting binary mixture, what's meant by quiescent? Effectively we say V star is equal to 0, right? And what is non-reacting? What is meant by non-reacting? Omega A equal to 0, right? Each of those, omega A, omega B would be 0, right? So we get dou CA over dou T is equal to DAB gradient CA, sorry, del squared, that is Laplacian CA, right? This is what is called as Fick's second law. I remember studying this in high school in a verbal as a verbal statement along with the Fick's first law, of course, but later on I found that students in subsequent years have not heard of Fick at all. Okay, now what does the second law say? It says something like if the first law were to mean that the diffusion mass flux is directly proportional to the concentration gradient, okay, the second law then says that the rate of change of the concentration is directly proportional to the second derivative of concentration, okay. So the mass flux is proportional to the first derivative, the rate of change of concentration is proportional to the second derivative. This is how the Fick's laws were formulated, but we can find that the first law that we started using cannot be derived from continuum point of view. It is stated as a law, okay. We said we needed that law because we wanted a connection between the mass flux, the diffusion mass flux, that is what else the species is doing other than going with the rest of the mixture. We needed a expression for that in terms of a primary variable, namely the concentration. So that was a constitutive relationship that the Fick's first law provided to us, and it can be obtained only if you get down to molecular level. You need to get into at least kinetic theory or quantum statistical mechanics, those kinds of approaches, in order to be able to derive it from first principles, right. So you now go through like a course like a physical gas dynamics in order to explain how you can get Fick's law, okay, and the two not necessarily very satisfactorily, alright. So that's a fundamental law, whereas the second law is something that you can actually find out from Molar conservation for a special situation of non-reacting quiescent binary mixture, right. So this is not as special as the first one. Good. Now while we started talking about mixing, that is diffusion, we have been stuck with binary mixture. Binary mixture is boring, okay, we need something more, right. So let's look at what to do for a multi-component system now, a truly multi-component system. In a truly multi-component system, when you say truly, that means it is not even binary, that is what it means. Binary is multi-component, okay, but bi is not multi enough, okay. So we want to have like at least 3, so you always look for the simplest situation. So 3 species becomes complicated, okay, for us. So in a truly multi-component system, that is more than 2 species, right. We can write the species conservation equation, okay, on a mass basis. Of course, that is to say an equivalent of this, particularly something intermediate between this and this. That means we will now say let's open up m dot a as rho a times v plus rho a capital VA. We will do that, but then we will start blinking because we don't know how to write rho a capital VA, which is JA, in terms of the concentration gradient, because Fick has not said this for us for more than a binary mixture, right. But we can go up to that point. So we will write this equation by just opening up into a mixture average velocity and the diffusion velocity. We will write up to that point, and then we will start blinking, okay. So not yet at the moment, okay. So we can go ahead. So we then say, and unless otherwise stated, it's always going to be mass basis from now on. We will never really go back to molar basis, okay. So we will now write this as rho yi for this is writing for the ith species, right. So rho a can be written as rho ya, alright. So similarly I am going to write rho yi over here for the ith species plus divergence. Again I am going to write rho a or yeah, rho A as rho YA, or in this case for the ith species rho YI, times, I'm going to write this as the mass average to mixture velocity V plus capital VI, right, is equal to WI, or can now try to do a few things. Pull out the rho, use chain rule, so you can write YI dou rho over dou T plus YI divergence rho V with the mixture average velocity plus rho V dot gradient YI plus divergence rho YI times capital VI is equal to WI. Okay, so the way it's written up is to group these two together, right, and then notice that this is just YI times this, so therefore this can go out, all right, and therefore you have a dou YI by dou T plus V dot del YI plus 1 over rho divergence rho YI capital VI equal to 1 over rho WI. This is good enough to begin with, because we can get some insights into what's going on. You can see that this together can say dou by dou T plus V dot del of YI, right. What is dou by dou T plus V dot del? That's the material derivative, capital D over dt, capital D over capital dt of YI. Okay, so in a Lagrangian frame of reference, you would simply look at a time rate of change of species mass fraction YI as far as this is concerned. Alright, so this is actually together then called the inertial term. Okay, this together is called the inertial term. Inertial term, of course, you can, in an Eulerian frame of reference, we notice that there is a basic change in the concentration because of with respect to time, as well as there is an apparent change because of its motion. All right, so this is the distinction between an Eulerian and a Lagrangian frame of reference. If you were to go with the particle, you will not know that you are moving, and therefore you will see everything as only a rate of change of time. That's what indicates your material derivative, right. But then you now step back and say, wait a minute, all the changes that I went through is because I was truly changing, plus I was also experiencing the world around me as I was moving. This is happening in our lives, right. So there is a lot of philosophy in fluid mechanics, you see. You start thinking about this, it is very intuitive. Okay, so if you now look at an Eulerian frame of reference, you can now identify this as the unsteady term like before, and this is truly your convective term. Right. Now the moment you see your capital VI, that's your mass diffusion velocity. Okay, that's the relative velocity of species I with respect to the mixture, right. So this is your diffusion term. And as before, this is your reaction term, right. So you always have to learn to read equations term by term and try to assign meanings to those terms physically, then mathematical equations begin to look like sentences in English, okay, or your favorite language, right? And these are basically words, okay. It so happens that these words are composed of spellings that are very jumbled looking from a language point of view, but that's all it is. The equation tries to tell you something, and it's a string of words that make sense, and you have to start looking at each of those terms like words that make sense, right? And of course, you know, you have to keep in mind these pluses and minuses. They're like the verbs and all the things that are thrown in between these meaningful words to convey the meaning for the sentence as a whole, right? So this is what we are essentially looking at for the species conservation equation. We still have a problem. We don't know what is capital VI vector, all right, but you have to keep in mind, now that you're looking at a truly multi-component system, this is one equation that represents actually n equations, and n could be pretty large, okay. It could be 5, 10, 40, 100, not more than that, mostly. Okay, so this is a equation that's actually consisting of large number of equations. Keep that in mind, okay. And then the next problem that we have is we have to start looking at a much more generalized version of Fick's law for a truly multi-component system that tries to relate your V to Yi, Vi to Yi, okay. And you might be worried, Vi is a vector, capital Vi is a vector, so it has 3 components, okay. So we are actually having 3n equations that we should be looking for, but fortunately if you are now going to be looking for Vi in terms of gradient Yi, all the 3 components are buried into just one unknown Yi, because it's just a matter of taking gradients in different directions for you to get your capital Vi, right. We hope that we will now be able to get a Fick's law to work for a truly multi-component system, but unfortunately it's not going to be as simple, okay. It's going to take some more time for us to get there. We will start doing what's called as the multi-component diffusion equation tomorrow.